My name is Ashok, and I'm one of the co-founders and the CEO of Integral. We are a local consulting company, and we focus on writing really good code and doing that in the automotive and transportation space. We have a monthly meetup that we host out of here on every second Tuesday, and we talk about different topics from kind of the tech ecosystem in Detroit to learning software development, especially if you haven't necessarily gone to school for it, to kind of nerding out a little bit deeper like we are today with my buddy here, Sean Olszewski.
Bingo! Very few people get that correctly.
It's because I follow NCAA and Krzyzewski's kind of similar. Anyway, Sean's here from Boston, so welcome to Detroit.
Glad to be here.
And thanks for coming here.
Happy to be here.
And Sean's going to talk to us about extreme programming, test-driven development, and a very interesting way to measure the effectiveness of how well your testing is going. So, over to you.
Yeah. Thank you for having me. So my name is Sean. You already know this. Today, I'm going to be talking about something that's near and dear to my heart, which is testing. And this is something I've decided to kind of go out to other communities and talk about because I myself am a self-taught developer. I originally went to music school. I was at music school. I realized I cared way more about technology than I did about actually writing music with technology. And I just found myself building a lot of software. When I had gotten my first job, because that had been my trajectory into the workplace, I was faced with lots of difficult questions to answer. Like, Sean, we had this deadline and it was missed. How do we know your program actually works? Like, how do we know it's not your fault we missed our deadline? And that's not a good position to be in, and that's also not a position anyone should be put into. So it was from that moment thereon that I just very aggressively started researching test-driven development, researching automated testing, just really beginning to understand these concepts and wanting to make sure that if other people were in that position or were about to enter the workforce, that they themselves were armed with this knowledge so that they could build good software, that they could know that what they built was quality, that they could be able to say, I've tested it, here's how I've tested it, here's how I know it works. So to me, this is a topic that gives me great comfort at night when I've shipped something into production because I know I tested it. I know that I'm confident in my tests. I know that what I did was the best thing for the features that I'm trying to build. So without further ado, I kind of want to introduce myself a little bit further. My name is Sean Olszewski. My last name is actually in Polish, that's why it doesn't read phonetically. I probably from the spiel I just gave you, you can tell I care about designing effective test suites. So I earlier in my career figured out how do I build a test suite at all? How do I actually automatically test stuff? And then once I had learned that, I kind of was like, okay, now I know how to do this. How do I do it effectively? How do I do it so that when I'm working with 5 people, 10 people, 20 people, 60 people, it's still valuable, it's still meaningful, and other people can adopt that code and those practices and those techniques and do something meaningful. I practice TDD daily where I work. I work at a company called Pivotal Labs. Pivotal Labs is an international company. We have offices all over the world. I work out of Boston and Kendall Square. We're a consultancy that practices extreme programming. Extreme programming is a way of approaching software development that takes all of the practices we consider to be good to an extreme, and it's there. Code reviews are important. Everybody should be aware of code changes that are happening. Extreme programming says let's have code reviews constantly so we pair program. We know that proving our stuff works is important. We should be testing all the time. Let's start with a test. Let's take that to an extreme and only write code if there's a test that accompanies it. Everyone owns code in extreme programming, so anyone is empowered to make changes to things. I really love working at Pivotal Labs because you work with a lot of like-minded folks who are interested in improving their software craftsmanship and really trying to make sure that we build something meaningful and something effective. And the last thing I wanted to share with you all tonight is I really test drive all the code that I write. I write scripts that help me manage my student loans. I write things that get the news for me that are just the way that I would prefer to do it. And I really do start with a test of all of those because it helps me design the simplest thing that I need to get going. And we all may know from experience, writing code takes forever. There's just so many things you could do, you could not do. When you start with a test, it forces you just to begin with the simplest thing, begin with the actual problem you're trying to solve. And it drives out the simplest solution. So I'm a little bit of a dogmatist, if you can't tell, because it makes me feel good about what I do. So tonight we're going to be talking about 2 things. We're going to be talking about this concept of signal-to-noise ratio, which is a metric for a test suite. And we're going to be talking about some testing patterns, which are ways that you can influence your signal-to-noise ratio. If you are newer to software development, or even if you're experienced, it's important to consider the idea that when we are building software and we are building test suites, we need to have an empirical and repeatable way to analyze if they're effective. Going back to the first point here, I care about something that's effective. Metrics are a way that we can achieve that. They're things we can observe, they're things we can influence, we can talk about them, we can have meetings about them, we can study patterns and improve them. So tonight we're going to be talking about one particular metric, and in my opinion the most important metric, which is signal to noise ratio. Feedback. Yeah, right. Another fun fact. So I said I went to music school. I actually went to music school being an audio engineer, and I would realize why I should be probably standing further away from the mic. And two other things. If you want to reach out to me on the internet, there's my Twitter handle Shevsky, and there's my GitHub Sean Arl Shevsky. If you want to check out some of the side projects I have. So let's actually define it. I've been talking about why it's great. I've been talking about why it's important. But what exactly is this signal to noise ratio? If you were to look on Wikipedia, or you were to look into like a computer science or signal processing textbook, you would get this definition. Signal to noise ratio is a measure of the desired signal to a level of undesired noise. I mean, that's fine and well when you're like being very quantitative with things, when you're actually doing like calculus at work. But it's also sometimes used metaphorically to refer to the ratio of useful information versus the amount of irrelevant information in some sort of exchange. So you'll actually see like social psychologists using this to talk about like forums where they're like talking about something meaningful like politics or like psychology or something like that. This matters for test suites and is a metaphor we can apply to test suites because it is a measure of how clearly a test failure indicates a specific fault or issue in your code base. Meaning, signal to noise ratio is a metric that you can use to clearly identify what actually went wrong when you have a test failure. That's what signal is. It's something that can be applied to an entire test suite, and it can be applied to an individual test. It's kind of nice in that it's composable with something big, and you can use it with something small. The kinds of tests that we might write, the kinds of ways we would validate our code, are going to influence this metric differently. And we're going to look at some examples in a little bit that will kind of give you a tool belt to utilize this metric in the way that you think is valuable. A quick definition of noise is important. And noise is really anything that obscures the origin of a test failure. Like literally anything at all. Like I've talked to so many different engineers who practice automated testing, and I continue to just grow this gigantic list of like what noise actually is. So this is like the most basic and general definition I can give you. And also, because of that, understand noise is subjective. Your experience in a tech stack might make something less noisy to you than it is to somebody else. And that's totally fine. Like you're never going to be 100% perfect all the time. As we say in Agile, perfect is the enemy of done. So just understand noise is going to be a little subjective, but there are some things that we can talk about that are generally agreed upon from the conversations I've had. The first being, if your test suite log is super, super, super long, that's pretty noisy. It's kind of hard to figure out what exactly went wrong because I have to like scroll through a lot of text. That's like kind of a basic mechanical thing. Like I don't know where to begin in a 10,000 line output to figure out where the issue actually happened. Does anyone here code in Node? Or like at all? If you use like Jest or like Enzyme or any of those like testing frameworks, like the very last thing it prints is like a 20-line thing that says like, Node detected an error. This is not an issue with Node. Do not email us and do not post on GitHub. And it's like, that's like the noisy, like what is the value of that every time my test fails? Like it's not. I've written scripts that remove that because it makes me angry. Another example of noise is a poorly chosen match or assertion. This might be a term that's new to some people in the room. And by a quick show of hands, who here like writes tests at all? Who here automatically tests or test drives? So maybe you're familiar with the terms assertions or matchers. So that's helpful. For those who may not know this term, it's basically the way you're trying to compare something. It's the way you're trying to like say like this should be this certain way. If you choose that incorrectly, then you may not know what's actually going on. It's usually valuable to compare an entire array to another array than it is to compare one item from that array to another item from a different array, because you can kind of get like an output that says like it should be 1 through 10, but I got 2 through 9. And you're like, oh, okay, I'm off by 1, as we often are. Another example of noise is if you have a bunch of tests and they're all failing together. Where do I actually begin to figure out where the test failure originated from? This is known as cascading test failures. We'll see a very concrete example of this in a couple of slides, so I won't spend too much time on this. And the last example of noise many engineers have agreed with me on is you don't actually know what you're testing. So when a test fails and you're looking at the actual test code, what are you trying to prove? Like what actually, what actually are you like trying to say is broken here? And so those are all the examples of noise I want to share with you today. I've been talking about signal and noise, and I just, after defining it, wanted to quickly talk about why it's important to measure as a metric. You've seen what it is, you've seen some things that you may have been bitten by, but Sean, why does this actually matter? There are 4 reasons for that. And these 4 reasons, I think, if you can pay attention to, even outside of testing, you're going to write really good code and build really good software. The first is if you pay attention to signal to noise, your test suite eases debugging, which I think is one of the main reasons as engineers we want to have a test suite. We want to have something tell us that our code is broken. And more often, and when it tells us it's broken, we want to know exactly where to go. Put differently, it's going to ease debugging by reducing the amount of stuff we have to search through. It's going to make it much easier for us to find the source of an issue. The second reason it's important to pay attention to signal to noise is it helps you gauge the balance of your test suite. By show of hands, who here has heard of like a balanced test suite or an unbalanced test suite? Okay, I'm glad I get to introduce you to the idea. So there's this idea of you have many different kinds of tests. Again, we'll see some. But some tests are only going to work on your UI. They're only going to prove that like buttons exist. They're going to prove you can type text into a text field. And that's kind of like a UI test. And that actually is testing a lot of different things at once. There's also different kinds of tests that say like maybe I have a function in my code. This function receives like a string as its input, and I get an integer as its output. That's more of like a unit test. A balanced test suite is going to make sure that you have a good ratio of, say, unit tests to UI tests so that you're actually covering all the different parts of your code, and so that you have signal into the various components of your code to see when you have a test failure, where did that failure actually originate from? Was it the function that converts the string into a number? Was it your actual UI code that didn't type into a text field correctly? We'll again see an example of this in the future, and I can provide a resource after the slideshow about the idea of balancing a test suite. Last and most certainly not least, if you are paying attention to signal to noise, either at the time you write a test, at the time of analyzing your entire test suite, you can notice when you might be over-testing your code. We want, as engineers, to test everything, ideally, exactly once. And the reason for that is we spend time running those tests, and we spend effort maintaining all of those tests. And while we may feel at the end of the day like we have more confidence in our code if we test the same thing 2 different ways, it is confusing as a newcomer to a code base to do that. And it's very expensive to ourselves and the companies we work for to be writing so many redundant tests. We want to find the right test at the start of testing anything for us to get confidence in what we're actually trying to build. Paying attention to signal to noise will help you do that because you're asking the question, what is it I want confidence in? And when this thing is broken, what is it that's telling me it actually broke? The last one, I think I said the last one was the last one, I lied, sorry. The last point is that if you are paying attention to all of this, you can write tests that will be resilient to refactoring and will actually guide the refactoring you're making. Who here has heard of the term refactoring? A lot of us have. For those who may be newer to the term, refactoring is essentially rewriting code so it does the same thing, but the actual code that does the task you're trying to achieve is different, usually because you're making it better. There's like a mathematical basis for the term, but that doesn't matter for tonight. A smell or a symptom of a poorly written test suite is that anytime you try to refactor your production code, your app code, the thing that actually you're giving to customers or users, if you're changing that but constantly needing to rewrite your test code isn't withstanding or guiding refactoring. And that's not great because that means you need to expend all this extra effort to just write code, to actually like ship features. So if you're paying attention to this metric, what will happen is you're noticing how you are observing the code that you want to be testing. And hopefully you're doing that in a way that is not going to change very frequently, or is not going to change unexpectedly. The 4 reasons why we should care are right here. I'll let everyone kind of digest that for a moment, and we will then move forward. So we've talked about what signal to noise ratio is. We've talked about why we should care about it. We see, based on what I've sort of talked about with testing and test-driven development, why, like, if you're writing tests a lot, you want to pay attention to it. Let's actually talk about how we measure it. And this I think, is my favorite part of this whole slide deck, because I feel it kind of grounds things in reality. So signal-to-noise ratio, if you were, like, doing math or you were doing some other field outside of software engineering, would be quantitative. It would actually be like a number. It would be like 1.0 or 0.2 or something like that. Unfortunately, like most things in software engineering, everything we do is qualitative, meaning we have to use 4 descriptors like low, moderate, high. After much discussion with like coworkers at Pivotal and people who practice test-driven development and XP outside of Pivotal, these are some of the definitions that are very agreeable. We're going to be applying this qualifier to like an entire test suite, for an example. A low signal test suite, when a test fails, there's going to be more than one area of your code base that is the source of an error. So when I run all of my tests together, maybe I'm like excited on a Friday afternoon and I'm shipping a new feature, I run my test and there's a failure. If my test suite is low signal, then I don't know exactly where to begin debugging. More than one part of the code is the issue. Concretely, maybe that test failure suggests I need to look at the network layer and my presentation layer. So if you can imagine like your code base as being a sandwich, your presentation layer is here, maybe your like network layer is here, down here you have something called your model layer. When this test fails, it could be in any of these three layers, anywhere. Like literally it could be my entire code base. I have no idea where this issue is. I know it broke, there's value in that, but I don't know where it broke. That's not great. This is a low signal test suite that has high noise. A moderate signal test suite is when there's one area that is a likely source of error. So if we were to continue to use that example, that presentation example, then this middle layer, the network layer, is the only thing that needs to be investigated when a test fails. It's moderate noise, like I don't know exactly what file, what class, what function I need to actually look into to begin debugging and fixing this issue, but I know that it's somewhere here. That's great. All right, I'm easing debugging. I kind of know what's going on. And then there's high signal, the ideal. A very specific area of the code base is the likely source of an error. And what that can mean is one function call. Perhaps inside my URL builder class is the source of this particular error. So that means when I have this test failure on that Friday, I get to go home on time and I get to ship code that I'm confident in because I knew it was this exact function I needed to fix. And oops, I like needed to cast something or I needed to like put an equal sign somewhere. So that's usually how I spend my Fridays. High signal is typically low noise all the time. These are the 3 kind of columns together. I just like to throw this up for people to kind of digest it for a moment. So all is fine and well. In that last slide, you probably always want to reach for a high signal test, and that's a natural thing we want to do. Unfortunately, and we're going to see by example why, you won't always be able to use a high signal test, which is to say sometimes you need to accept noise. Sometimes the right thing to do is accept a little bit of noise, knowing that you're not going to have the fastest possible time to identify an error in your code, but if you're being intentional with picking high signal, moderate signal, and low signal tests, you're going to reduce it nevertheless, and that's still valuable than not doing it at all. Part of the reason why we can't have high signal tests all the time is because high signal tests don't always, like by nature, are very small in scope, and they won't prove that everything is working the way that we need to, and that can be okay. Again, we'll see some examples in just a moment. So I'm going to ask for help handing out. I have some code examples that we're going to be going through. I'm going to have Cole and Amber come around and kind of hand out some things. What is on the paper in front of you is going to be on the slides, but I wanted to give everyone the opportunity to, if you were interested in like continuing to learn this stuff afterwards, you have this. But also in case you needed a little bit more time to go over the code examples, you have the code right in front of you. There's a chance we don't have enough, and I apologize for that. So if the person next to you doesn't have one, if you would be open to sharing, that would be awesome. But again, this code will be on the slides. You can follow along at least with the slide deck. I don't think I've said this yet, but all of these examples are going to be in Swift. If you've never written Swift code, you're missing out on a fantastic language, but also these are not concepts that are unique to Swift. It kind of reads like most modern languages, so hopefully you can follow it along. If you see a slide or you just have literally no idea what's going on in the code, feel free to raise your hand and I'll be more than happy to explain it. Swift has some opinions about certain things that are unique to it, and maybe I've found in the past that influences people's understanding of the code. It seems like we've handed out all the code examples, so I'll keep moving forward. All right, so how do we do this thing, Sean? How do we influence it? We're going to talk about two techniques tonight. These are applicable. These are immediately applicable. If you're not test driving your code, if you're not even automatically testing your code, you could turn around and immediately start using this stuff. And for the sake of science, at a minimum, I encourage you all to do so. The first technique we're going to talk about is about something called test doubles and how we use them. We're going to explain and define test doubles in just a moment, but I wanted to give everyone an overview of what we're about to talk about. There's then also the way that you choose to test your code, the test patterns you use to prove that your code is working correctly. That's the second way that you're going to influence your signal-to-noise ratio. And these are the biggest things you can do to influence your signal-to-noise ratio. So let's talk about test doubles. Who here has ever heard of a test double? Who here has ever heard of a mock? A mock is a kind of test double. So we already have a good understanding of things. I find the language we use to describe things like mocks, like spies, unfortunately ambiguous. There's a resource I will be providing to all of you that I find to be phenomenally clear in disambiguating it. But nevertheless, if you've heard of a mock, if you've heard of a spy, if you've heard of a dummy, a fake, or a stub, you've heard of a test double before. A test double is a stand-in for something that would otherwise be real in the execution of your program. In other words, a test double is useful in testing when you need to substitute a real class that you wrote, a real struct that you wrote. There are 5 kinds. A dummy, a spy, a mock, and a fake, and a stub. It's not important for you tonight to have a very clear and concrete definition of each of these. We will be talking about one in just a moment, but I like to throw this language out so people can kind of be exposed to it as someone who's been testing for a while, because it's your utilization of this that is a very that kind of determines how good you are at writing tests. And it takes a lot of practice. I'm still learning and practicing this stuff over 2 years later of automatically testing everything. So I've been saying test doubles improve the signal-to-noise ratio of your code base, and there are 2 reasons for that. They let you isolate a test subject from dependencies. The test subject is what you are actually testing, so it lets you isolate it further. So if you think about it, if something breaks, what you are testing is actually isolated from what broke, so it's not affected by it. And it lets you do something called, it lets you create interaction points. It lets you actually create points that let you observe how your program works. It lets you observe how your code is actually behaving, and it lets you control it in a different way. Who here has used a stub or heard of a stub before? So like you may like stub something out to return a particular value, right? That's a control point. Who here has used a mock? You would probably say like expect this mock to have been called, like to have this function called on it. You're creating an observation point. And it's through your utilization of those that you improve your signal. At the same time, if we overly do this, if we're constantly saying stub this value and return it, if we're constantly saying expect this object to be called with these arguments, then our test suite becomes a restatement of the code that we are actually writing, which isn't great. We're actually then testing like how we coded something versus what we were the task we were trying to actually achieve. So try to minimize this to the best that you can. This was a ton of theory. So let's actually like look at some code. Let's actually like dive in and begin to actually like see how this stuff works. So I'm about to show you some examples. Depending on what page you're looking on, you'll see what's on there. Like you can just flip it around. There's only 4 pages. See a hand come up.
Oh yeah, isn't there also the issue that test doubles may not accurately represent the real life objects or real life APIs or such that they're meant to emulate?
Yes, that is exactly an issue with them as well. I'm glad you brought that up. The current project I'm on at work, I was working on a feature that needed to save things in the database differently. And like by differently, I mean like, oh, it was like related data, like we needed to do some crazy thing because we were storing like the order or something. And the testing strategy up until then had been basically using mocks to say like, oh, expect this to be called a certain way, and like that's good enough for us. We know the real one has the same interface. But like I like wrote that test and I made it pass, and it like still didn't persist. And I was like, oh, like this strategy doesn't give me enough confidence that when the user enters data and they like navigate away from the page, that it actually saves, because it doesn't. So then I needed to write like a more fully featured integration test, and to actually like prove when I hit this endpoint, it saves it in the database, and I can retrieve it on another network call. So yeah, that's exactly another reason to avoid them. Is you have to know how the thing works in order to create the test double to prove that it works.
Yeah, and if you're interacting with APIs you don't control, then there's no way to know for certain how that'll work.
Exactly, because another team can change the behavior on you tomorrow and not tell you. To bring it back to this example, we're about to look at an example from a side project of mine, which is a music app. You don't really need to know anything about music or, in fact, this code base to get a high-level understanding of it. But I was kind of coding this one afternoon, and I sort of noticed that in one of my tests, I was using a real instance of something. I was using a real struct, and the thought came to my mind, like, if this struct broke, like, I'm kind of curious how my test suite would like show me that this thing was broken. So this is the test suite when everything is passing. You should have some examples of these code in front of you, so if it's difficult for those to see, maybe because you're in the back, maybe because black is challenging for you to read against, you should have it in front of you. And so the key thing to take away from here is, here's my test suite, everything's green. This is an Xcode if you've ever had the misfortune of using that program. Here's the start of my test suite. Again, like it's okay if like Swift doesn't matter to you. The key thing I want you to pay attention to is right here I have something called a chromatic note mapping, and right here it has this interface. That's all you really need to know right now. If you've ever coded in like C++, C#, Java, Kotlin, Go, you have structs. They're basically just like something that has data and methods. And a thought came to my mind, which is, what happens if I break this? Because I'm using a real one up here. This test is not isolated from a breaking change in this class. So if the behavior of this ever changes, this test should probably fail. And lo and behold, when I change a 1 to a 0, everything breaks. I have 4 failures in the test up here, which is not the chromatic note mapping, which has 2 failures down here. This is pretty noisy. I literally changed 1 character in my program, and 6 tests failed. If I didn't know how to navigate this code base, if I didn't understand much about like what this app was actually trying to do, I wouldn't really know where to begin debugging. So I would spend a lot more time than someone who's familiar with the code base trying to figure out what actually broke. Also, I would then need to know that I had to change a single character to make the entire test suite pass, which if you've ever had the misfortune of working with C, you would realize that single quotes are different than double quotes, and that's 8 hours of looking on Stack Overflow to fix the issue. So this isn't great. So I have a very noisy test suite. I have 6 failures from a single character change. So what can I do? Well, I can use a test double. The test double I use in this case is one called a fake. And a fake is a test double that exactly mimics the thing that it's doubling, the thing that it's replacing. I created a class called MIDI note mapping fake. It has the same exact interface. It does the same thing. And this same breaking change is now isolated to only this test suite. I have 2 failures here, only 2. I have a much higher signal and much less noise as a consequence of that. I know exactly what file to begin debugging with it. Like most things in engineering, this comes at a trade-off. And that trade-off is, to make this fake, I had to write all of this code. And that's not great. Fakes, and in fact all test doubles, require maintenance. And as you see, they significantly improved the signal. Again, I went from 6 failures to 2. But that improvement in signal came at needing to write all of this. Even if I was using like a framework. Fun fact, Swift doesn't support frameworks for a reason that's not important. I would still end up needing to code most of this logic using like stub and return, or expect this to be called with this. Like I don't get around that. The problem is the same, just expressed differently. And this kind of sucks. I don't want to do this all the time. So earlier I was talking about like we need to balance signal and noise. And that's one of the reasons why we need to do that. Because if you're constantly trying to go for very high signal, that usually comes at the expense of a lot of maintenance. And that could be okay. Maybe that's actually what your team has. Maybe you have the effort and the skill set to do that, and that can be totally fine. In the context of that test suite, because I'm the only maintainer, I decided not to. I was like, this isn't worth my time, because every time I change that chromatic note mapping class or any other thing that has that interface, I then need to rework this fake, and I'm really uninterested in doing that when I'm working on Saturday in my spare time. So that's the first technique that we've learned about influencing signal to noise, using these ideas of test doubles. I'll have a resource at the end you can look at that not only defines these test doubles, but actually goes through an example of creating every single one of them and like using them in a testing environment. So if that was a lot to digest at once, there will be more resources for you. The second technique is the testing pattern selection that you have. Who here has actually heard of a unit test? Who here has heard of an integration test? Who here has heard of an acceptance test? These are categories of testing patterns. They are not the testing patterns themselves. And that's fine, because they all achieve different things. That was a fly. And one thing I like to do when I talk about testing is these are ways we can automatically prove things work, but it's insufficient when you're writing tests all the time to say, like, let's just unit test this. Well, what kind of unit test do you actually want to write? Not everyone's hand went up, and that's totally fine, because I want to appeal to everybody. Really quick, I just wanted to ground us in the idea of a unit test and an integration test. And this is also my favorite thing to argue with people over, too. So if you disagree with me on any of these points, like, feel free to come chat. But very quick, like the attributes of each of these kinds of tests. Unit tests are usually very isolated. Integration tests are not. Integration tests prove lots of things work together. Unit tests, one thing is working correctly. As a consequence of that, unit tests are usually unaffected by cascading failures. That example I just gave you, that is 100% a unit test. But it was affected by a cascading failure. Integration tests, by definition, are affected by cascading failures, meaning if I'm proving that my entire network layer makes a network call, something can break in my network layer and everything else fails as a consequence. Unit tests have this language of being like a white, gray, or black box test. And what that basically means is how much information do I have about the thing I'm testing to prove that it works. If I have no information outside of the public interface, outside of the functions that I'm calling, outside of the fields that I can access normally, that's a black box test. On the other hand, if I have complete knowledge about how this thing works on the inside, that's a white box test. We'll see examples of these in just a moment. By definition, integration tests have no idea how things work. They just like make the network call and check a response. Or they are like a user typing into a field and pressing submit. They have no idea how the app works. Unit tests, because they're small, because they're looking at very few things together, are moderate to high signal. Integration tests are the inverse. They are low to moderate signal. If you have a moderate signal integration test, you are rocking, because that is a very hard thing to pull off, and it's very valuable. And again, that's because it's the scope of what they're actually testing. We typically would say that something that has high signal has low noise, moderate signal, moderate noise, low signal, high noise. And so it kind of makes sense that these would be opposed to one another. So those are kind of like the quick rundown. If you like Google each of these terms, you're going to get a lot of different blog posts saying a lot of different things. This is, when I talk to people about it, this is generally the most agreeable thing that I've gotten out of people. Unfortunately, automated testing and software engineering is a very opinionated and ambiguous space when it comes to language. We're going to talk about 3 of these tests tonight, but to kind of break down this dichotomy a little bit more, we're going to be looking at some testing patterns beneath it. Black box tests are one, collaboration tests are another, contract tests are an integration test, and UI tests are as well. I've sort of been using some of this language already. Out of curiosity, who here has heard of a UI test? Or just quick show of hand. Okay, some of us have a contract test. Okay, some of us, fewer of us, but some of us have black box test. Okay, and a collaboration test. No one knows of a collaboration test, yet you're all writing them. Cool. So let's talk about some testing patterns, and let's look at some code again. Again, you have an example of this in front of you if it's difficult for you to see the screen or you want to go slower than we're going. So this is a black box test. It's a unit test. This is like the most isolated and high signal test you could possibly write. And what this test is saying is, given a date, I produce a string that represents that date. That's a very important test to write. a surprisingly challenging test to write because depending on where you live in the world, depending on where your product ships in the world, the way you format a date is very different. This is just using the traditional way we do it in America. This test is isolated because if you look over here, if you look towards the top, all you see is we create something called an axis value formatter. That is the subject of this test. It just exists by itself. This could actually just be a function we call and it would be fine. This code comes from an app I was working on that needed this to be a struct, so we made it one. Right here, lines 18 and 19 on the slide, that's actually the thing we are testing, the string for value function. All we're doing is jamming in an input, and then right beneath that, we're just proving the results we get are what we expect. We have no knowledge of how this thing works, so it's black box. It's isolated because it has no dependencies. It's just doing this thing. And it runs very quickly because it's just like, transform this thing, go for it. Like code like that runs very quickly. It's not affected by cascading failures because anything that it is actually using comes from the standard library, and like that's not going to break. Like if that broke in your program, you should, I don't know, you should talk to the language designers because that stuff gets so thoroughly tested by people who are so much smarter than me that it just impresses me. So this thing is not going to be broken by anything else. High signal, low noise, black box test. Collaboration tests. This is my favorite testing pattern to introduce to people because I have such strong opinions about it, and also I work with a lot of engineers who don't have the language to describe it. A collaboration test is any test you use, any test you write, which uses a test double to prove something is working correctly. The term collaboration comes from the idea that what you are proving is correct is the test subject's usage of a dependency. You're proving your test subject collaborates with a dependency. And the way that you do that is by, for example, looking at the method calls that your test double receive. If you're using a mock, which in this test there is a mock, we're proving right here that this method got called. And we're proving it received these arguments. So that's not actually proving that I made a network call, which is the spirit of this test. It's actually proving that I called something. I'll take a step back. Has anyone here ever done iOS development? I think there's a little bit of explanation necessary. So very few people in this room have done iOS development. All this code is proving is that something called a view controller, which is essentially the same thing as like a web page, once it loads, it makes a network call to retrieve some information. So you can, if you've never written iOS and don't care, you don't really need to care about this like setup method. The only thing you need to pay attention to is the fact that we have a mock HTTP client, and that inside of our test, we're proving that we called our mock HTTP client correctly. I've been sort of espouting how we need to be careful with our usage of test doubles. This is a time when it makes a lot of sense to use one. The reason for that is this is not an API we own, to your point, Allison. This is actually just like literally a public API you can use for getting the price of cryptocurrency. On top of that, network calls are non-deterministic, which means that the same inputs can and will produce different outputs, literally depending on things we can't control. It's like effectively random. So if we want a test suite that is repeatable and gives us clear indication that something went wrong, it stands to reason that in this particular test, we don't want to be affected by that, because that might say we're not loading data after the page loads. But that's not actually what's true. I saw a question. I'll make sure it's available afterwards if that's the case. My apologies for that. Good to know. My apologies. One reason why this is a very high signal test is in being isolated from the mock client, the signal you're getting is that this client was actually called correctly, which is like the highest signal you could possibly imagine, but is also the implementation detail. Like you're actually observing the interface that this class happens to have. That can change, that can and will change. So if you ever change the mock client, you then need to change this code. You need to rewrite this test, which isn't great. But this is an example where we're willing to accept that. We're willing to accept that maintenance cost of needing to rewrite it because, again, we don't control the internet and we don't control this API. And we need to prove that this works otherwise. So that's a collaboration test. It's a high signal, low noise, white box test because we know the entire implementation of what we're testing. The last test we're going to look at, the last testing pattern, is a contract test. So this is actually that thing we just looked at that was mocked. This is the test that proves it makes an API call and downloads data from a cryptocurrency API. For those who may be newer to the term contract test, a contract test is one you use when you're trying to prove that an interface you're using, generally an abstract one like a REST API or maybe even like a Java or C# interface, has certain behaviors. It works in a certain way. And the certain way we're expecting this API to work is that we get a 200 status code when we make a correct call, that we get back 3 data points for the particular date range that we specified, and not only that, but that it's ordered. Right here, like we're indexing into an array and proving that like the first item is the start time and the last item is the end time. So that like proves the contract of the interface, which is to return sorted values by day, is respected and fulfilled. This particular testing pattern is not isolated from breaks beneath it, because there's all sorts of code beneath the client that actually go on to make sure we make this network call correctly. And this test like could fail for that reason. It could also just fail because the internet's down. Like that actually happened on a project I was working on once. We got DDoSed and we didn't have internet for a while. And so we're like, oh, like our tests are just failing because they can't make a network call. Whoops. This is also an asynchronous test. So if anyone was ever curious what those look like or heard about that being a challenging thing to test, it can be. This is how lines 4 and 28 are how we achieve that with this particular testing framework. But I also like to call that out with this. This test is black boxed because we literally just create the API client on line 6 and we just use it. We know its interface, which is public. That's all we need to know. And we know that we're going to get some value back. And because that is a public thing, we don't need to do anything fancy to make it work. There are some things not on this slide that are declared like in the file above that I omitted for brevity, such as the start and end time. But just pretend that there's like a date declaration there. So we're coming up towards the end of the slide portion of the presentation. We kind of have gone through a lot, and a lot of this is like kind of theoretical, and I've tried to ground an example with all of you. But I wanted to just kind of like give a high-level overview as to what we actually talked about. So first and foremost, we define signal-to-noise ratio mathematically, kind of metaphorically, and then how we actually talk about it in terms of automated testing. We reviewed why that's a concept that matters and why it's something that we should care about. What are the stakes in like knowing this and not knowing this? We defined test doubles, something that a lot of us are familiar with through different language, and we saw how they influence signal-to-noise ratio. We then went through a refactoring example, a rewriting of code to maintain behavior, where we improved the signal-to-noise ratio of a test suite. We reviewed how unit and integration tests are different, how they influence signal-to-noise ratio differently, and some sub-patterns within unit tests and integration tests to help us write better test suites. And we now find ourselves here. I wanted to offer up resources because I think this is not a topic I can summarize, or rather I can summarize it, but I cannot give you like the deepest dive in all of the world for this, because this is something you can continue to practice forever. I've been automatically testing code for 2.5 years at least, probably closer to 3 years, and still like I find new stuff every day. I still find new testing patterns and tooling and techniques. So I wanted to provide some things that have been valuable, some things I've actually referenced in the creation of these slides to help you all out. Links on a slide deck aren't great, so I will be sharing this out as a PDF through Meetup, so you can all access it and actually click on those links. But if these are like titles you want to take a photo of and look up, by all means, I think that's valuable. The first link on here is kind of an obligatory reference I need to give. It's like the canonical book on test-driven development by Kent Beck. He's one of the signers of the Agile Manifesto, if you've ever heard of that. It's short, 67 pages, I think. If you have the time on a weekend, you can probably just bang it out. The second is an article written by the Director of Engineering Practices for Pivotal Labs. It's a deep dive into test doubles. I mentioned this earlier. It's like, what are those 5 test doubles we wrote? Why would I use them? If I wanted to hand roll one and not use a framework, how do I use that, and why would I do that? And he also goes through refactoring examples of going from like one to another to another. It's like the best article I've ever seen on it, because these are very, like, again, loosely defined terms, loosely explained terms. The third thing in there is like a Bible and a reference. It's like 1,200 pages. It's like you can only buy it hardcover. It's called XUnit Test Patterns. A lot of the code is in C# or like Java. It goes into like all of these topics we've talked about tonight in like chapters. Like there's like 3 chapters on test doubles and like writing them and like why you should pay attention to them. That language of interaction points and observation points and control points was something I got from that book. But it's like literally if you didn't know anything and you read that entire book word for word, page for page, you would just have everything in your mind. And that the last one there is really only applicable if you write iOS or Apple code. However, if you wanted to see someone who is strong in test-driven development, is strong in automated testing, has thoughts, and you're interested in seeing how a very strong type system forces certain testing patterns, it's a great blog to check out. If I was to give this talk with JavaScript, there'd be a lot different code and a lot different explanations for why things were done. But Swift is a language that has strong opinions to the contrary of JavaScript. So there's Joe Mazzalotti. Last but not least, I want to give a shout out to Integral for inviting me out to speak. They're a wonderful company. I've worked with a few of them at Pivotal. If you care about like writing good code, you care about automated testing, about XP, about TDD, these are people who would happily teach you, who would give you these opportunities to work. They're all about welcoming people who are new to code, new to software development into the workforce to help them, to help those people and to help build great software for everybody. They're currently hiring. You can talk to Ashok in the back if you are interested in finding out more. Yeah, it's been a pleasure to work with you all in the past, and I can really speak to the quality of the code they write. Secondly, they run Integrate Detroit, which is a workshop, if I'm not mistaken, or boot camp. How would you describe it?
Yeah, it's a boot camp finishing school. There's a couple of students here, Al, Tom somewhere too.
But yeah, so if I've met many people who finish boot camps and are like, all right, like I've done like Node.js for like 4 months, great, and I want to get a job. Well, there's like so much more about software development you can't cram into a boot camp, like collaborating, like version control, like testing even, and it's a great opportunity for you to like learn those things outside of it in a safe space that's really focused on getting you into the workforce. So check them out. And that concludes like the slide portion of everything, and we now have some time to have questions, have answers, those code examples that maybe you didn't have enough time looking over, you may have questions about, we can go over. And also pull up some of these, like some more of the code if you needed more of the code to understand it, because I have these available on my GitHub as well. But I wanted to open the floor now for any questions you all might have. I'm happy you asked that. Like, so a contract test it can be both, is the answer. It's kind of interesting. So the example I showed was an integration test. I omitted an example from that music app I mentioned where I have unit tests that are also contract tests. If it's of interest to the crowd, I could actually show you some contract tests that are unit tests. Really quick, I might actually do that. The reason why it can be both is the abstract contract that you are implementing. Oh, I have Google Chrome open here. I can't see anything on my screen. The interface that you are implementing and testing can either be like a REST interface, which you need to communicate with asynchronously. So it's an integration test because it's like I need to make a network call to retrieve that data. Or it can be like an interface in C# or Swift or Java to actually that you need to code.
What if you use the test double for the test column?
So if you did that, then you would be writing a collaboration test, and you would be saying like, the test double that I would use might be a fake, so I just get a result back, or it could be a mock. And you're basically just saying like, I've called this thing in a predictable way, which like is only like half of what you are trying to prove. The other half is when I call this thing and I get a value back, that value is like returned in the way that I predict. But what a test double won't tell you is that the second half of what you tried to do worked, because unless you put that into the test double, which would be weird, yeah. I'm going to try to, let's see if I can quickly pull this up. This is an example of a contract test that is a unit test. I'm going to try to, I didn't expect to show this tonight, but very quickly, you'll notice it's like anything, any MIDI note mapping will make this pass. And what it's doing is it's going through and running the same test on everything in this array. everything in this array, which is right here, is a different implementation of that interface. Who here is familiar with like C# interfaces or Java interfaces or protocols? So a good number of us are. I will say this is an advanced pattern. So if you're not familiar with this or it's a little over your head, that's okay. But basically, each one of these implements the same pattern or the same interface, which is right there, any MIDI note mapping. And right here, we're only exercising what's declared inside of that interface. And if all of them implemented this interface correctly, they will all make this test pass. So that's another example of that's how a contract test can be a unit test and an integration test. In this case, this will never make like a network call, so this can never be an integration test. It's just a unit test. Did that answer your question?
So I guess this is the contract with
Yeah, it's the contract would be like the interface in that case. They are both interfaces. Like you have a REST interface, and then you may have like a code interface. And like the code interface just says, I have these methods, and that's it. I don't have an implementation for them. REST actually says the same thing when you think about it. It just says, I have these endpoints. You can use these verbs on me, and you'll get a certain value back. But there's no guarantee of how it's implemented. It could be Python, it could be Java, it could literally be both Python and Java. We don't know or care. Oh, yeah, sorry. The question was, what is the difference between, or can a contract test be a unit or an integration test? I'm going to jump back to my slides, which I think are right here. Cool. I see a question right there.
What are your thoughts on BDD, and do you like to start with integration tests or unit tests when you're working on a feature or story?
You asked two questions I care a lot about. So the first question is, how do I feel about BDD? I prefer it. And in fact, this whole test suite, and all the tests in this app I've been building are, this is BDD. This is behavior-driven development. I provided a resource earlier called XUnit Test Patterns. BDD is contracted with XUnit a lot of the time. The difference is a lot in how you choose to use language to describe what you are testing. BDD is not a tool, it's not a framework, it's an approach to writing tests that uses a shared language between engineering, product teams, and business teams. You'll notice in these tests that there is music domain language. If anyone here is a musician and you've heard of MIDI, then like you might gather like, okay, this is doing something with MIDI notes, which like will eventually be turned into sound. Like that's the advantage. Like if you are a musician in this room, you kind of get the gist of what this code is about. So BDD is this idea that you figure out what those terms are. You figure out like the way you want to express it in English, and then you literally write a test suite around that English. So you see here, like, describe any MIDI note mapping, it will default notes. Like it's using this language that is very clear and easy to understand if you're familiar with this domain. You can be brought up to speed in this domain. And literally, it's just isolating things based around the behavior the code should have. There were some XUnit examples in the code, or in the slides. Right here. This is an XUnit test. And the key way you can tell that, if you ignore the fact that it says XC up there, it's just a function. I have it like this kind of like test underscore blah, 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 blah. This, you can still sort of achieve the same thing here. You can still use like that language, but BDD kind of takes that language approach and tries to create tooling that utilizes that ubiquitous language, that shared language of communicating like a test specification to non-technical people. It's a lot harder to do that with XUnit. And traditionally speaking, XUnit is more concerned with like validating your code works, like either by implementation or others, whereas BDD is more concerned with calling out what behaviors your program should have, like the higher order tasks that should be achieved, and like creating tests that clearly call that out. It is largely semantical, I will be very honest with you. But I found that when I was able to like sort of navigate the difference between them, I found that I wrote tests that were much more understandable by non-technical people. I had a moment at work where, because we had done that, and we had written like a lot of like UI and journey tests just like prove workflows in your app can be done. A very high-level executive walked over and he looked at it and he was like, "Oh, okay, I kind of get this. Like you're expecting there to be a text field on the screen. Okay, like all right, cool, that makes sense." That's all it's supposed to help those people with. It's not supposed to teach them how to code or write tests, but kind of gives them insight into how you're validating things, which is an invaluable tool to build a good relationship with non-technical teams in your organization. To your second question, which is, do I start with integration tests? Yes, I usually practice something called outside-in TDD. So what that would mean is I'm starting at the outside. What is the outside? It's the interface somebody has to use something. So if I'm adding a new feature to an app, the app I'm working on currently, the last feature I added allows someone to add like multiple citations to something. It's kind of like a report-making tool. So, okay, I'm going to start with like a UI test that literally taps a button that doesn't exist, and then I'm going to expect there to be a new text field that I know won't be there, but it's going to expect it to be there. That test is going to fail. Then I'm going to say to myself, okay, now that I have this outside written, what's the next test I can write to prove that this is working correctly? Well, I'll then like look at like the components that manage those text fields, maybe create those components, and then I'll write tests that create an interface for those components, and I'll make them fail. And then I'll like continue and repeat that process all the way down. Once I have all these tests failing, I'll then work my way back up, writing all the code that makes those tests pass. And that's outside in. There is the inverse, there is inside out. I start all the way down here and work my way up, and that can be valuable for like technical discovery. That contract test I wrote for the cryptocurrency API, I did that. So I was like, this is an API I own. Their API docs were terrible. They had like broken English, so like I had to kind of guess on certain things. And I was like, all right, let me just like get this integration working. I know that in this case, all I need is like a number and a date. That's pretty reliable. The risk you run if you start inside out is you may like you will find new things as you're working your way back up that you maybe didn't account for down here. And then that can cause you to have to go back down and rework it. That can be okay. Like maybe you need to do that technical discovery because you just have that ambiguity. Did that kind of answer your question? Cool.
And the rest outside in is now you're tied to ambiguity, and now you have to have a layer on the outside.
Yeah,
So
yeah.
Why not do it that way?
Exactly. Yep. Everything with its trade-offs. What other questions might we have?
Can you give any perspective to at what levels you actually push for some of these integrations, like extracting out to your CI, and like do all levels of all of these things you mentioned run all the time, like as you're building, or is some of it built into the CI, or what's the perspective you might want to share with us?
Absolutely. I'm going to drink a little bit of water as my voice is hoarse. So the perspective I have there, CI should basically run like all the tests all the time, because it's also like not a machine you're developing on. Who here has heard of CI, or continuous integration? For those who are newer to the term, it's a very good practice that many decades of software engineering have said we need to do. And basically what you do is you have a dedicated computer that's not yours. Anytime you make a code change, that computer is going to like build the code, run all your tests against the code to make sure that like it works on everybody's machine. That makes like improves you like checked in dependencies that you downloaded for that feature or something like that. You can also run it all the time, so you can constantly know your code is always healthy. Anyway, that's why if the point of CI is to like make sure your code is healthy, you should be running all your tests all the time. I will again refer to my current project as like an interesting one because we have an engagement where we are teaching like more junior developers like these practices. So we want to make sure that they're remembering to run all the tests. So we have a pre-commit hook that runs some of the tests, but not all of them. The reason for that is Git has this interesting timeout server side where if you like say you want to like push your code and share it with everybody, it will only let you like keep that connection open for a certain period of time. What that means is you may not have enough time to actually run all of your tests before when you go to say like git push and share all your code. So our acceptance tests, which were like typing text in all these fields and like navigating different pages, would cause that timeout to occur. So we couldn't run those tests then. So we just ran our unit tests. So for our pre-commit stuff, our pre-push stuff, we just run our unit tests. We expect everyone to be running them like as they're actually developing, as they're actually adding new features and making changes. I've been on projects where we wanted to make sure. What was that example? There was one test that was like we only wrote it to prove like a third-party dependency was available because they were typically very flaky. And so what we did in our CI was, and I need to take a step back. There's a common pattern in CI where if those tests fail, you don't deploy what was checked into CI. And the thing you are deploying would be reviewed by like product folk or like your stakeholders, the business people, to prove like or to show them like, hey, here's what we built. Check it out. Let us know if it's what you wanted. So if your tests fail, you don't want to give it to them. Something went wrong. So we had a test that didn't gate that because all it said was momentarily like our third-party dependency was unavailable because they didn't have very high uptime. So that would be an example where I don't want to block anything, but I want to write that test anyway because I don't trust these people. They don't deliver things on time, and what they deliver doesn't work. Was that insightful? What other sorts of questions might we have? Well, I'm still going to be hanging out if any of you have further questions and would rather talk to me one-on-one. But I want to also extend a huge thank you to Integral for having me out here, Bamboo for having me, to Detroit for welcoming me into the city, as I've been here many times. They're very friendly folk here. And to all of you for sitting here and promising to be better software engineers by learning how to automatically test. Thank you all very much. You can find me on Twitter at __Shevsky __. Here's my email and here's my GitHub if you want to check me out further. Thank you all very much.